A 2-liter sample of O2 gas was collected over water at a total pressure of 785 torr and 25 degrees Celsius. When the O2 gas was dried, water vapor removed, the gas had a volume of 1.94 liters at 25 degrees Celsius and 785 torr. Calculate the vapor pressure of water at 25 degrees Celsius. For any sample of gas, there is a relationship between the quantity of that gas, its temperature, its pressure, and its volume. This relationship can be represented by the ideal gas law, or PV equals nRT. Within this law, there are 4 other laws, one of which is Boyle's law. Boyle's law states if quantity and temperature are constant, volume and pressure of a gas are inversely related. This can be written as PV equals nRT constant, which can then be converted into P1V1 equals P2V2. Because we are finding the vapor pressure of water at 25 degrees Celsius, we are then solving for P1. So the equation can be then converted into P1 equals P2V2 over V1. Now the pressure and volume values must be plugged into the equation to calculate the pressure of O2 gas. P1 equals 785 torr times 1.94 liters all over 2.00 liters. We are left with P1 equals 761.45 torr. However, we are only trying to calculate the pressure of the water, so we must subtract the partial pressure of O2 gas from the total pressure of the original mixture to get the partial pressure of H2O gas. This is represented by PH2O equals P total minus PO2 gas. And when we plug in the values, PH2O equals 785 minus 761.45, we get 23.55 torr. Because the original problem has digits with only 2 significant figures, the final answer comes out to be 24 torr.
A 5-gram sample of one of the substances listed in Table 6.1 was heated from 25.2 degrees Celsius to 55.1 degrees Celsius, requiring 133 joules to do so. What substance was it? Here, I wrote out Table 6.1, which can be found in the book, with all the substances and the specific heats of the substances to help us calculate what substance was used in the question. Q equals mc delta T can be used to solve for the specific heat. Q is the heat required, M is the mass, C is the specific heat, and delta T is the change in temperature. Right here, I am plugging in the values that were given to us in the problem, the heat required, the mass, and the delta T, Tf minus Ti. Next, I condense the equation by subtracting the initial temperature from the final temperature. Next, I multiplied the 5 by the 29.9. Finally, I divided 133 by 149.5 to get a specific heat of 0.889 joules per gram degree Celsius, which rounds to 0.89 joules per gram degree Celsius. The substance, therefore, is aluminum solid. It takes 585 joules of energy to raise the temperature of 125.6 grams of mercury from 20.0 degrees Celsius to 53.5 degrees Celsius. Calculate the specific heat capacity and the molar heat capacity of mercury. In order to find the specific heat of Hg, the equation Q equals mc delta T has to be used. The problem identifies mass, change in temperature, and the heat. Plug in to solve for C. Now plug in your givens. 585 joules as Q, which is equal to the mass 125.6 grams, times the specific heat, which is unknown, times 53.5 degrees Celsius minus 20.0 degrees Celsius. Next, we're going to simplify the equation 585 is equal to 125.6 grams times the specific heat times 33.5 degrees Celsius. We are going to condense it even more. 585 joules is equal to 4,207.6 degrees Celsius times gram times the specific heat. I multiplied 125.6 times 33.5. Finally, divide 585 joules by 4,207.6 to get the specific heat of Hg to be 0.139 joules per gram degree Celsius. To find the molar mass, all you have to do is look at the periodic table since mercury is acting alone. Since mercury is not combined with anything, to find the molar heat capacity, all you have to do is take the specific heat, 0.139, multiply it by its molar mass, 200.59 over 1 mole, is equal to 27.9 joules per mole degrees Celsius. So your final answer will be 27.9 joules per mole degrees Celsius because of the three significant figures.
An unknown element is a nonmetal and has a valence electron configuration of N(s)2 and p4. A. How many valence electrons does this element have? B. What are some possible identities for this element? C. What is the formula of the compound this element would form with potassium? D. Would this element have a larger or smaller radius than barium? E. Would this element have a greater or smaller ionization energy than fluorine? Valence electrons are electrons located on the outermost shell of an atom, and they can be shared with other atoms or participate in forming chemical bonds. This element would have 6 valence electrons because in the given configuration of N(s)2 and p4, there are 2 electrons in the s orbital and 4 electrons in the p orbital, and 2 plus 4 equals 6, leaving us 6 valence electrons. When looking at the periodic table, elements that have 6 valence electrons are located in the 6A group of elements, which include O, oxygen, S, sulfur, Se, selenium, Te, tellurium, and Po, polonium. Elements in group 6A have a -2 charge, so any of the elements from part B when formed with potassium would result in the formula K2X, where X is the symbol of the unknown element. This element would have a smaller radius than barium because when looking at a periodic table, atomic radius decreases from left to right and increases going from top to bottom. Barium is farther to the left and is at a lower quantum level, meaning that it has a smaller radius. This element would have a smaller ionization energy than fluorine because ionization energy and atomic radius are inversely related, so as one increases, the other decreases, and vice versa. Fluorine would have a smaller radius than this element, which means that its ionization energy would be greater than that of the element.